Buongiorno, good afternoon. How are you? Do you have any question for me? No. Remember, I want questions. Okay. It's a session, and but I will try to stimulate you. So, first of all, I have been required to inform you, but I'm sure that you are more informed, better informed than me, that the new deliberation of the Council of the Degree Program regarding your attendance to the lectures means that you are required to attend 100%, and which means that if you don't physically attend, you are required to watch to the presentations, to the videos of the lectures, which, by the way, should be made available also in, besides my website, should be made available also in a repository that is accessible to you. I still don't understand how it will be recorded besides my recording, but hopefully it will be there. But in any case, if it's not there, you have the video on my website. By the way, I put online the video of 2 weeks ago, I think. And still it has a technological problem because I think there is only the audio, there are no images. I hope that I can solve the problem with this video. Be patient with me. You know, when one moves to another system, it's always a problem. And I hope that today everything is fine. I still have some doubts about the audio. So this time maybe that you have the figures, the video, and not the audio. Let's hope that it's not like that. And if it is like that, I will try to record another audio on the videos. I don't think you will be able to see in the video my face because I can't see a camera here, and I checked it seems that it's not, but you will see the screen, which is the most important thing. Of course, it's important also my face, but the screen is more important. So if you have any doubt regarding your attendance to the lectures, you can ask me, or better ask your office of reference. Actually, I don't do anything regarding attendance. I just check the list, and today I saw that there are 2 students missing, but I'm not doing anything. I thank you very much for letting me know when you have to go out earlier or when you cannot attend. I really appreciate that. And don't worry, usually I don't have any problem with that. I am used to teaching in a university where it's not compulsory to attend the lectures. So usually I see at my lecture only 10% of the students. So it's absolutely not a problem for me if you leave earlier, but I appreciate very much if you can leave. So I think that's it. Okay, so last time we started with an introduction to what is climate change. Now we have to go into more details. So what is the purpose of the next lectures? The purpose of the next lectures is to quantitatively understand climate change in terms of modeling, how climate change is modeled. Because climate models give to you the necessary information to evaluate the impact on Earth. It is like that in all the disciplines that are related to climate change impact. For instance, in hydrology, I am used to get the information from hydrological modeling and through this information evaluate the social impact and economic impact, etc. So the same for you. In order to better profit from this information, it is essential that you know how the data are generated, how the climate is predicted. Of course, you don't have to go into fine details, but you have to learn the concepts, because knowing how the data are generated allows you to better understand the reliability of this data. Remember, there is uncertainty. We already discussed about that. And in order to fully understand uncertainty, it's required that you understand how this data are derived. And also, you need to know what is the best use that you can make from this data. And your role is particularly important because you are directly related to human health. And therefore, this is an essential information. I'm not sure how much you are educated about modeling, so I will try to inform you in a way that is, as I think, close to what you are used to in your discipline. But of course, if there is something that you see that is maybe not really appropriate in terms of, for instance, of level of complexity of what I teach, I hope it's just a transition, and then if not, we will close the doors. So I think, okay, let's close them. If you can please close it. But before modeling, because modeling is indeed starting models may be boring, I would prefer to start by giving to you an example. This is what I usually do also in engineering, when teaching engineering. I prefer to give examples. So I prefer to show you how the data can be retrieved. This is another essential information. How the data can be retrieved and how the data can be used with reference to a case study that may be your case study. So let's start with looking at the products from models before going into the details of models. We start from the end. Okay, it's a bottom-up approach. This is something that is very popular today, you know, reverting the classical approach to education, not top-down, but bottom-up in any dynamics related to education. So let's forget then my website for a second, and let's go into this website, which is the Copernicus Climate Data Store. You see bottom left, Climate Data Store, and it's by Copernicus. If you Google Copernicus Climate Data Store, you get into this web page. Copernicus is the European service for weather and climate forecasting, which is based on computations, activities that are carried out by the European Center for Medium Range Weather Forecasting, ECMWF. Okay? And the ECMWF has also an headquarters in Bologna, because they needed to acquire a new supercomputer, and they made a call in several countries to check where it was more convenient, and Italy won the call, and in particular Bologna, because they had headquarters available at the Technopolo that was dismissed from previous industrial location and was renovated to host the supercomputer. And by the way, the supercomputer of ECMWF, together with the Leonardo supercomputer, again in Bologna, they are up to now the most powerful supercomputers at the global level. And still, I don't think they will resist a lot in this qualification, because, you know, supercomputers are continuously growing up. And basically, they are growing up in order to satisfy the demands required by artificial intelligence computation. But still now they are the most powerful supercomputers at the global level. If you get to Wikipedia, to the list of supercomputers, you see the updated list. So basically, Copernicus is an extremely interesting source of information. You see that I am already logged in. You will probably find a login button instead of my name there, for sure. And in order to log in, you have to register. Registration is for free. Okay. So let's look at Copernicus. And just 1 second. I'm sorry. Let's browse it a little bit. One premise. These data are really huge. These are big data, because they are the result of global simulations. So they have to convey a picture of weather and climate at the global level. And we will see that this requires a lot of computational capacity, and they produce, this model, a lot of numbers. And therefore, basically, extracting these numbers is not easy. And in order to extract these numbers, very often, you need to know something about coding. We will discuss about it. Okay? Actually, coding, especially now with the advent of artificial intelligence, has become something that is more relevant with respect to the recent past. Because, in order to manage a huge amount of information, usually you don't have ready-to-use software, commercial software. Like, for instance, if you think about Excel is not able to manage a huge amount of information. And therefore, you have to resort to some platforms that are less user-friendly and therefore require some knowledge of coding. This is to say that my advice for you, given that you are working in a field where also the amount of information is tremendously increasing, also because there is, fortunately, a trend towards open data, open science, I mean, my advice to you is don't refuse to get some basics of coding. I will try to instill to you this passion, okay? But before coding, let's look at the applications, because the Copernicus data store, the climate data store, gives to us some applications that are ready to use. For instance, let's click on some of these windows. Climate Pulse, let's open it and accept. Okay, what you see here. So this is the surface air temperature anomaly, but let's look at the graph, which I think is more interesting. This is the global surface air temperature, and you can see here an ensemble which in gray, the gray lines are the graphics of the progress along the year of the global temperature. So for each day, you have a number for the 30 years from 1991 to 2020. So the gray lines are the graph of the global annual temperature from 1991 to 2020. And the three colored lines are 2023 in yellow, 2024 in light red, and 2025 dark red. What can you see? You can see that we are, with respect to the 30 years from 1991 to 2020, we are at the upper limit. But on the other hand, you can see that, and this was expected, looking at the progress of the data, 2025 is probably less warm than 2024. And still, it's a bit of a question on the behavior of 2025 with respect to 2023. Okay, and the graph here basically is a graph that refers to the surface air temperature anomaly of the 4th of November, so 3 days ago, okay, 2 days ago. And it's the anomaly with respect to the baseline period, 1991-2000. And here you have the calendar. You can select November 3rd, for instance. You see that it's a bit different, November 2nd, etc. Okay, this is one example. Let's look at another example here. This is the global temperature trend monitor. It's another example that is interesting. This is depicting how close we are to reaching a global warming of 1.5. You may have heard that in the Paris Agreement 10 years ago, several countries, the head of state of several countries convened and developed a strategy, agreed a strategy to limit the global warming to plus 1.5 with respect to the pre-industrial period. Actually, we are not going to be successful in that. And in fact, you will see here in this graph, you see from 1970 to 2025, you see the progress of the global temperature. And by making a linear regression, I think you know better than me what is linear regression, but fitting a straight line to the data of the past 20 years, they predict that, the plus 1.5 will be reached in May 2029. And of course, you see that in individual years, we already reached the plus 1.5. But as we know, when we look at climate, we have to take the average over a period of about 30 years. So this is why when we take the average, we can say that we are not yet at plus 1.5. This is another interesting application. These figures can be downloaded, and you can also download the data. One interesting thing, if you look above here, so there is the application, the frequently asked question, the glossary, and the source code. Let's look at the source code, because what is the source code here? It is the code that you have to use in order to get the data from this platform. As I said, in order to download the data, you have to apply a source code, okay? And the source code is a program, it's a computer program. And what is the language? You may know that there are several languages that can be used. There are tens of them. The most used today is the most up to date until some artificial intelligence will take over very soon, I think. But today, the most used is Python. Okay, this is a Python code. So Python is a programming language, and it is the most used because it's extremely versatile. It is really powerful. You can make graphs that are really excellent. No comparison with the graphs that you make in Excel. Some comparison with the graphs that you can make in MATLAB, maybe that you are used to MATLAB in order to manage data. And why a good graph is important? A good graph nowadays is extremely important because today communication, dissemination, and getting the trust of the public is, as you know, extremely important, especially in medicine, but not only in medicine, also in climate science. In engineering, usually, I don't know why, but in engineering, people tend to trust the engineers quite a lot. But there are other disciplines, and one discipline is climate science, and the other discipline, I think, because I'm not an expert, is medicine, where the trust of the public is a bit, I'm not sure if it is stable or decreasing. And therefore, making a good presentation, it's extremely important. And this has been proved. So keep it in mind. If you can produce good graphs when you present your thesis and when you make an interview, when you discuss with your patients, it's extremely important. So this is an example of a Python code. We don't get into details now, and I just want to show you that there are sentences written here. A program is just a sequence of instructions, and the instructions taken one by one are extremely simple. They are addition, multiplications, or maybe computation of the logarithm if they are complicated. And what makes the code complicated is that there are many of them, first of all, and the code is useful because instead of making one computation one by one, you make the computations in a list. And if you have to repeat this list of computation, it's a matter of a fraction of a second. And there is a second thing that makes the code complicated. It's the language, because we have to know the instructions. So what is the word that I have to use if I want to say to the code that I want to compute 2 plus 2? So you need to know the language. It's like talking in a foreign language. So you have to learn a foreign language. But the good thing is that the glossary is very limited. It's not like a language, you know. And therefore, of course, it requires some adaptation. And what looks also to me a bit, a bit of fun is that in my career, and my career is not extremely long, my degree was gained in 92, so 33 years ago, I had to learn at least 1, 2, 3, 4, 5, 6 languages. And, you know, learning 6 languages is not easy. Fortunately, the concept is more or less the same. And the concept is, basic concept is that in a code, you have to learn the functions. So again, the name of the function sum, the name of the function square root, and you have to learn how to write cycles and conditions. Cycles, because the code is useful when you have to repeat computations several times. Okay, like climate models, usually we run them 1,000 of times, and therefore we have to repeat. The second condition is what makes artificial intelligence. So conditions are the tools that the computer uses to take decisions. So if that's true, yes, then I go this direction. No, then I take the other direction. By the way, artificial intelligence, I think it's not a good term because artificial intelligence, we really discussed it, it's not intelligence. Because, for instance, I give to you an example. Artificial intelligence does not learn from its errors. And if it doesn't learn from its errors, it's not intelligence. But artificial intelligence is very powerful because it is an automatic repetition of tasks. So if it is supervised by a real intelligence, is extremely powerful. And it gives to you, with respect to a couple of years ago, a number of tools that is much larger. So don't refuse to learn it. And besides learning, try to understand it, because probably in the near future it will be the new code, because it is extremely simple. It is user friendly. Okay, so now let me just give you an example of a computation, of a case study, which may be relevant to you, that I can develop with this data. So let me go to my website, where if you go to our page of our lectures, you will see an additional link. It's a case study, trend of Lyme disease under global warming. Let's see. So first of all, this is developed in Google Colab. What is Google Colab is described here. I go down. Okay, Google Colab. Okay, what is Google Colab? Is a free. There is also a section under payment. If you want to use several computational resources, you have to pay. But basically it's free, and what I'm showing to you, I didn't pay. My university didn't pay, so it's to me it was free. Is a free cloud-hosted environment for running Jupyter notebooks without local setup. So you can write and run Python and other languages in your browser without requiring in your platform a special setting. So it is extremely useful. I learned it just a couple of months ago because I have a student that he is a super nerd. And so basically I learned from it. The name of the student is given, by the way, because I put it up front, because it was an excellent demonstration on how indeed the source of education is two ways interaction, so between the teacher and the student. And also this applies to the interaction that I have with you. But I need your question for learning, okay? So basically, is integrated in Google Drive, and the advantages are listed here: zero setup, free hardware accelerations, and the Google Drive integration, easy collaboration and sharing. You know, I'm using it for teaching, so more than that, it's not possible in terms of collaboration and sharing. Battery is included because the libraries, all the software is already included. You don't have to make any particular setup, and it's reproducible, and it is open. So let me just show you a possible application of Google Colab, who can take the data from the Copernicus data store, the climate data store, and allow you to make analysis. For instance, this example is something that I consider really meaningful, maybe because I am very exposed to ticks. I like mountaineering, I like running across the mountains, and every year I take some tens of ticks. And so you know that the ticks carry a lot of diseases, and the most popular probably is the Lyme disease. It's the most popular because it has a high incidence, and we will discuss it in detail. We don't discuss it in detail today. It's not a communicative disease, but it is a tick-borne disease. The Lyme disease is not particularly concerning. I mean, It's not a pleasure to get it, but if the person is in a good shape with a lot of antibiotics, you can treat it. It's not a real concern. But there are other illnesses. By the way, this list here was derived with artificial intelligence, just to let you know. And of course, I'm not including here the links, but for the information that is provided, artificial intelligence, now most of them, remember that there are many artificial intelligence engines, not only ChatGPT, but there is Gemini, and also there are those that are used in the Middle East, which are very, by the way, Grok 1, Grok 2, and Grok 3. They are very powerful. And the most rigorous give to you the reference. And keep in mind, checking the reference, so fact checking with artificial intelligence is essential, because artificial intelligence, I say it again, I also told you 2 weeks ago, by definition, it's wrong. By definition, because it takes here and there and puts together information without an intelligence behind. So the intelligence must be yours. So you have to check the references and check if what is reported is true, and you will discover many errors. But with fact checking, artificial intelligence is really great. So the Lyme disease is a pathology, but the list is long. And what is important to see the regions, because the pathology is carried by the ticks, but the ticks must be infected. They have to get into their body the bacteria or the viruses that bring the pathology. And usually these bacteria, viruses are exchanged between the ticks and the wildlife. And therefore, depending on the region, there are ticks possibly infected by a pathology. And in other regions, there are different pathologies. So what is interesting here is to look to the pathologies that are widespread in Europe. And I mentioned to you, I already said the Lyme disease is not very serious. I mean, of course, as I said, it's an illness. So, and it's anyway a concern. And I wanted to mention to you the encephalitis, TBE. This is very serious. It's very serious because, it can cause the death of the person quite easily, also a young person is in a very good shape. And the problem with these diseases is diagnosis. They are difficult to be diagnosed because they are not frequent diseases, and the symptoms as such are not very well codified. So very often, it's the last investigation that in the hospital we make. The wife of one of my colleagues really passed for a very, very tight fissure, we say in Italian. We say è passata per un buco molto piccolo, because she got an encephalitis by ticks and during a trip in the mountains in the Veneto region. So in Veneto, indeed, there are some spots where the ticks can carry encephalitis. And as I said, she passed really very bad weeks. And at a certain point, she didn't fully recover, by the way, because there are neurological damages for that. So it's interesting to study the connection with climate change, because it's clear, it's very clear that after climate change, there has been an increase of the incidence of these illnesses. You know that the fact that there is correlation doesn't mean that there is causation, because sometimes there are confounding factors. So maybe that the ticks are increased not for the increased temperature. Maybe they are increased also for increased temperature, but other factors like, for instance, the population of wilderness, because in the past, there were less deers, less wildlife, because, in the past, there was a more intensive practice of hunting, and many changes occurred. And also the number of forested areas in Italy, for instance, is increasing. Italy is not affected by deforestation. It's affected by the decrease of cultivated land, and therefore means an increase of forestation, increase of wildlife. For instance, in my region, in Emilia-Romagna, the ticks were not a problem up to 20 years ago. And then with the proliferation of the deers and small deers, the ticks increased in number. But of course, climate change seems to have an influence, and the influence may be due, and there is a description later on, okay? But basically, it may be due to the fact that with the increase of temperature, there is an increase of the life cycle, duration of life cycle of the ticks. So we are exposed for more months because the ticks typically they proliferate in the warm season. So with the longer extension of the warm season, there are more ticks. Here there is a description of the climate data store. We jumped through it because we already discussed it, okay? And there is also a description of the data that we are going to use. Here, I am using past data. I'm not using future projection. Here I am retrieving data of global warming over Europe because I want to see over Europe how much global warming was indeed impactful. And therefore, instead of looking at the global temperature, I want to look at the temperature over Europe. Of course, you may say, but 2 weeks ago, you told us that there is the website, the World of Data, Global World of Data, that gives already the data that are you looking for. Of course, but I want to make an exercise, but by looking at the data. Because, for instance, now I am giving the coordinates of Europe in the code that you will see here below. But if you're interested in the Lombardy region, for instance, you give the coordinates of the Lombardy region, and you can see the increase, the global warming in the Lombardy region or the city of Milan. I refer to all of Europe because it was just a motivation of ease, because I didn't have a map of Lombardy to superimpose over my graphs. So this is the only motivation, but I could make it now. I could change the coordinates and refer to the Lombardy region. So as I said, we are using observed data. What kind of data? What are called reanalysis data. What does it mean, reanalysis? When we make a measurement of a weather variable or a climate variable, we refer to a point. So rainfall is measured in Milan, in Bologna, in Rome, in Genova, in Florence. I'm naming the Italian cities where we have the longest rainfall series. But actually, nowadays, we have information on the land that is distributed. It's not only point information, because we retrieve this information like vegetation cover from satellites. And therefore, the need emerged for getting also climate and weather variables in a distributed form. How they are distributed? They are distributed by reanalyzing the data. And basically, we fit an interpolation model, which allows us to interpolate. If we have a measurement in Bologna and a measurement in Milan of rainfall, we not only have these two measurements, we have also measurements in between. We make an interpolation, we fit with some analytical functions the data so that we can estimate rainfall also in between, maybe every 3 kilometers. This is possible. And this interpolation is also done with climate models, because climate models know how to interpolate by taking into account the variability of climate and weather. And these are the reanalysis data, and they have a resolution of 5 kilometers. It means every 5 kilometers, I have a measurement. And you understand, these are global data. ERA 5 is global. And they measure temperature, wind velocity, pressure, humidity, or air humidity, and many others. So can you imagine how many numbers and how difficult it is to manage them? It's impossible to think of managing these numbers in Excel. It's absolutely, they are petabytes, you know, we have megabytes, gigabytes, terabytes and petabytes, and every time you add a zero, okay? Every jump you add a zero. And we have petabytes, but not a few petabytes, hundreds of petabytes of data. Okay, so this is the reanalysis, and this is an example of how the data are reanalyzed. ERA 5 is very popular because it's very long. It covers the period 1940 to today, up to 2 days ago. And as you have seen, I have got the global temperature on November 4. So, I mean, the numbers are really, ERA 5 is really very powerful. What is Colab? We already learned it. So, look at how Colab allow you to work. This is the code that I've written in Python, which can be run step by step. And first, we need to download the data from the Copernicus data store. Okay, this is the first step of the code, which can be run by clicking on the arrow here. Okay, they want just 1 second. Google, of course, wants that I get access to it. This is something that I forgot to tell you. So you need to get access to Google in order to use Google Colab, of course. I'm using it to the computer of the room, so it's the first time that I run it here. It's like I run it in your PC. The problem is that I have to remember the password. Let's see. And then if the password is successful, then there is the call to the phone. So 1 second. I understand the security problem with this, with the artificial intelligence. On the other hand, it's something that is really, okay, so let's run it. And basically, the first thing that we have to do in a Python program is to install the libraries. The libraries are the list of the functions that you need to use. And so based on your application, you have to use different functions. You may need a trigonometric function. You may need, for instance, a tool that allows you to work with matrices in several dimensions. And therefore, the installation of the libraries, you see that Google Colab is loading all of these functions, and it's loading in the cache. Sometimes I get the server, I don't understand why, but I understood that it can be resolved by rerunning it. Remember, when you work with coding, what is important is efficiency and the final results. It's not important to understand everything. The important thing is to make it working. Okay, good. Now, this is the instruction to get into the climate data store and download the data. The data are monthly averaged temperature over Europe at high resolution. I'm running it. And nice thing. Let's see. Yeah, I forgot. I'm sorry. I forgot a step. This is why it gave to me an error. Okay, let's rerun it again. I think the reason is that I need to put them in order. So okay, perfect. And now they want the address of the climate data store, which I have to get here in my account. Here it is. So my profile. And then you see here there is what they require. The URL, I copy and paste. It's already there. Sorry. Okay. and the K let's do like this. Okay, once that you put the K here, now I'm not moving forward step by step because it takes some time. You can move forward. The first thing that we can do is to plot a graph of the temperature over Europe. For instance, on January 1st, 1979, I downloaded the data from 1979 to today, to yesterday, okay? And this is a map of over the temperature over Europe for the January 1st. And then I can move forward. This is another graph that I can derive, and it's the near surface air temperature anomaly for the year 2016 with respect to the whole period 1991-2020. Let's move forward. Other steps. This is the European monthly climatology from 1991 to 2020. It shows to you as an average over Europe the progress of temperature for each month, and the variability is the band, the green band, light green band is plus minus 1 standard deviation. It gives an idea of variability. Let's move forward. This is the progress of the European yearly mean temperature from 1991 to 2020. So clearly you can see the sign of global warming even in Europe. And basically the increase is from something close to 10.4 degrees to something that is around 11.4, 1 degree. It's more or less the increase that we observe at the global level. Now the question is, given this increase of temperature of 1 degree, what is the expected increase of the cases of Lyme disease? Of course, we need now to find information of the correspondence between temperature and the number of cases. So again, artificial intelligence with the references that I checked, and in particular, these are the reasons why a warmer temperature can give an increase of the Lyme cases. There is an increase of tick survival during winters. There is a longer tick activity season. There is an accelerated tick development rate. And there is an expansion of the suitable habitat to higher elevations. There have been some studies. A study published in the Proceeding of the National Academy of Sciences is a journal with a very good reputation by Levy et al. And they found an increase of about 20–30% of the number of cases for an increase of temperature of 2 degrees. So 10–15% more cases with an increase of temperature of 1 degree. There is another study, 2018, on the journal Ticks and Tick-Borne Diseases. It's a good journal, but not as good as PNAS, the previous one. And they reported an increase of 8–10% per each degree. So what is a rule of thumb that we can derive? About 10% for each degree of increased temperature. And actually, keep in mind one thing. The relationship is not purely linear, because we may expect that for increasing temperature, we have a lower incidence of the increase, of course, because there is a limit to the concentration of ticks. Like in any natural environment, there are equilibriums. So clearly, asymptotically, there is a max to the number of ticks, okay? And therefore, the relationship is not linear. Linear means that the 10% increase for each degree is the same forever. It cannot be the same forever. And there is also that ticks need humidity. as well as warmer weather. And, you know, there are also public health interventions, hopefully. Therefore, I mean, this is purely a rule of thumb, but if we apply this rule of thumb, this is, in percentage terms, what you may expect in terms of yearly increase of Lyme cases in Europe from 1991 to 2015. This is something that is on average. Of course, we also should look at the areas, because the average doesn't give you an idea of the distribution. Of course, the increase of cases is not expected in the cities. It's expected in the wide areas where the cases are already occurring. So, moral of the story, which is finished here. I wanted to show you the importance of getting climate predictions in order to instruct health policies. Second, the importance of using the available tools up to date, and these tools are continuously improving. There is continuous innovation, and therefore the message of beware of artificial intelligence, because it is something that will for sure bring, again, more innovation. Last message, these developments are necessarily based on coding. So it depends on your attitude, your target. If you want to make research in medicine, so if your target is to deliver innovation, to find new solutions, beware that I believe the importance of coding is really massive. Of course, if you have other targets, it's less important. But now, I mean, computation, artificial intelligence, coding are really becoming very relevant. Okay, that's it for this part, this example that I wanted to give. Questions? Okay, so let's close here. And yeah, I go out. And we can close this. Yeah, Copernicus Climate Data Store. My suggestion for you, explore this site. It can give to you several ideas. There are ready-to-use information that you may use for your career, for developing your career. And my recommendation, try to elaborate a vision and try to get the information and education that you think will be useful for your future. Okay, let's close this and let's go back to my website, which disappeared. So let's open another browser. Okay, here we are, albertomontanari.it and lecture notes. Good. So we introduced climate change in my last lecture. Now let's jump to the third. Sorry. Climate modus. Just 1 second, because I am missing a link. Let me see. I think I forgot to put it here. I am missing a link which I will include in the webpage of this course. Okay, and the link is a lecture that discusses the Earth system. In order to build a model is a falsification of a system, is a digital twin of a system. Falsification, of course, is not the proper word, but I think it is meaningful because indeed the models are false. But anyway, the model is a reproduction of a system through mathematics, through mathematical relationship. In order to run a model, not only to build a model, in order to run a model, we have to gain the knowledge of the system. So given that we are talking of the Earth system, it's required that we discuss some basic elements of the Earth system. Let me open the PowerPoint that is on the bottom here. And don't be concerned that the lecture is I will forget the mathematical details of it, or not all of them, but most of them I will skip. And let me open this PowerPoint. Okay, F5. Let's see. Good. Let's see what you see. Perfect. It's fine. I think that probably in the video you will see my view, and my view is 2 slides. Anyway, the Earth system. So, first of all, it is a complex system. The Earth system that we are trying to describe includes all the processes, all the dynamic processes that are taking place within the Earth sphere, where the Earth sphere includes also the atmosphere. And there are several processes. And what are describing, what are governing these processes? These processes, I call process something that governs the flow of matter or quantities. So flow of energy, flow of water, flow. There are several processes, several flows of matters in the body of the Earth, in the atmosphere. And these processes, these flows are interacting with each other. And this is a typical example of complexity, because when you have several processes that are linked with each other, they are often used as an example of complexity. What does it mean, complexity? It is not easy to give a definition of complexity. We can say that also the human body is a complex system. But how can we define it? Of course, also in the human body, there are several processes interacting with each other. But this is not a definition. I like to define complexity as the behavior of a system that makes the system not completely predictable. So it's predictable to some extent. Again, I define complexity as the behavior of a system that makes the system itself not completely predictable. And therefore, there is uncertainty. And I think the human body, indeed, is not completely predictable. Like, for instance, a river is not completely predictable. Otherwise, we wouldn't suffer from floods. If we suffer from floods, it means that we cannot fully predict them. And so what is the consequence of that? The consequence is that in order to devise strategies, risk mitigation, or therapies, or engineering solutions, I need to account for uncertainty, because uncertainty means limited predictability. Okay? And therefore, I need to account for it. Okay, it's a complex system. And in order to study the Earth system, traditionally, we tried to look at these processes one by one and separately. So there is a science called climate science that studies the climate. There is a science called hydrology that studies the water flows. There is a science called economics who studies, and social sciences at large, who study human processes. And typically, they are analyzed separately, like medicine is analyzed separately. In doing that, we forget about the connections. If we don't study climate in connection with economics, you understand that it's difficult to find a solution. This kind of integral approach is also called an holistic approach. We say that an approach is holistic when we approach a problem by considering all the implications and not separately each one of them. And this is the modern trend in science: interdisciplinarity, multidisciplinarity, interdisciplinarity, transdisciplinarity. You know the differences. Multidisciplinarity means that you take results from different disciplines. Interdisciplinarity means that people working in the different disciplines work together. So it's not just putting together the result. Interdisciplinarity means working together. Transdisciplinarity means that you generate a new discipline, which is the synthesis of several disciplines. Transdisciplinarity is a dream. In fact, today we talk about interdisciplinarity. Okay, we already forgot about multidisciplinarity because it's something that basically we give for granted. We are working on interdisciplinarity. What is the problem? The problem is that interdisciplinarity in the current systems for devising solutions, for recognizing the merit, is not recognized. So to give you an example, if you are an expert of several disciplines, at the end of the story, you are not recognized by any one of them. And this is a problem in the academia, for instance. Interdisciplinarity is not recognized, okay? So let's try to, anyway, to embrace this trend to, and then to study the Earth system holistically. And however, sorry, I go back again with the slide. However, it is convenient to try, for classification purposes, to split their system in components for classification purposes. It's an aid to interdisciplinarity. And these different components, we call them the spheres. So now you realize why the atmosphere is called atmosphere. And you realize why the hydrosphere is called hydrosphere. And you realize why we talk about the technosphere, which is the sphere that collects the anthropogenic processes. Okay, first premise, which is essential. The Earth system is closed. There is only one matter that can flow in and out from the Earth plus atmosphere system. What is this matter? Energy. Remember, the Earth system exists because there are flows. What is the fuel for this flow? Is the sun. So the energy of the sun gets into the Earth system. And it's the only matter, if you exclude meteorites or UFO, okay, it's the only matter that can get into the Earth system. So the fact that it's closed is a big advantage. The fact that, for instance, water is conserved unless you split the molecules of water into hydrogen and oxygen. This is what happened over Mars, by the way. If you don't split the molecule of water, it's conserved. So there is no possibility to destroy water. Okay? And why it is an advantage, in fact, it is a closed system, because you can apply conservation laws like conservation of mass. In fact, an essential law that we use for modeling water flow is conservation of mass. So these are some examples of spheres. Atmosphere, geosphere is the sphere of the geology. Can I ask you a favor? Because it's difficult for me to teach if you talk, because I listen what you're saying, because this is something that I realized in conferences. Sometimes I stood in the back and I thought nobody listens to me. And then the speaker came to me and you said this, this, and this, because it's very strange, the sound. So if you can just limit, I'm not saying that you don't have to speak, but just not speak continuously, because otherwise I get distracted. I'm sorry, it's a weakness of me. So atmosphere, geosphere, biosphere, hydrosphere, and then there are other examples, the cryosphere, the lithosphere, the pedosphere, and the technosphere, which is the sphere of the humans. Okay, so it's interesting to look at the connection among these spheres in order to move towards an holistic view. So how can we look at the connections? This is an interesting question. So how can we understand what are the connections between the atmosphere and the hydrosphere and the technosphere? It is interesting to look at the flows between one sphere and another. For instance, let me take this example, the carbon cycle. the carbon cycle is an excellent way for studying the connections among spheres. And the carbon cycle, indeed, is extremely important for climate. And you see here a representation of the carbon cycle. I mean, we are not interested in the fine details, but we are interested in the fact that is linking several spheres, including the sphere of humans, the technosphere. Because, as you know, by burning fossil fuels, we are increasing the flux of CO2 in the atmosphere, and therefore we are increasing the concentration of CO2 in the air, and we are affecting climate. By the way, keep in mind that carbon is fueled by the sun. So fossil fuels are originated by vegetation that in the very past far was died. And so vegetation that grew up thanks to the energy given by the sun, this vegetation died, was collapsed over the soil, and then for tectonic movements and for after volcanic eruption, this vegetation got embedded in the underground and decomposed to originate natural gases and fossil fuels. So basically, the fossil fuels are a storage of energy that came from the sun in the past. It's embedded into the earth. By extracting the fossil fuels, basically we are extracting from the inner of the earth carbon that has been stored in the past, was generated, it's a reservoir of energy, and we are releasing this carbon in the atmosphere. This would happen anyway, probably, because, you know, it's through volcanic eruptions. It's something that happens anyway, but in geologic times. So along very long times, actually we are accelerating the process, and therefore we are affecting the carbon cycle. So if you describe these fluxes of carbon, and also you need to describe the social evolution, the social dynamics, if you want to describe them, we can describe the links between the different spheres, and we can describe the system with an holistic view. So it is a very interesting perspective to look at the flows of matter. And there are some matters that are more important than others. Carbon today is extremely important. And in order to decipher these links, now there is a huge investment of resources, financial resources in research projects, and a huge investment of human resources and knowledge. Maybe also too much, you know, because of course we follow trends, but we also deal with processes that we don't fully understand. Another possibility, another cycle, which is very well known, it's the water cycle. If you study the fluxes of water, you look at the connections between the spheres, and the fluxes of water are related to the fluxes of carbon. And therefore, I mean, these cycles ideally shouldn't be studied in an isolated way. We should study the carbon cycle in connection with the water cycle. The water cycle is something that we know very well. And also, I think that you probably will study some of it in the course of ecosystems that you will probably, I'm not sure, but probably some of you will attend the next year, and they also will describe, will see something about the water cycle. I studied a lot the water cycle, so I know it quite well, but I don't want to go into the details because I don't think that you need to know the details. Just be informed that there are models describing the water cycle, continuously improving. And another interesting cycle, another interesting flow of matter is given by energy exchanges. It's very interesting to study the energy exchanges. And I think that it would be even more interesting to try as I said, to put these cycles together, one idea that I am exploring in my research activity is to study the movement of water in terms of energy content, associated energy. And why I got this idea. Usually we study the movement of water by describing the flow of water. So the flow of water, which is originated by an energy exchange, and the flow is, we study the movement of the mass of water. Why I think it would be interesting to study the movement of energy through the water cycle? Because when the water cycle impacts people, it's through energy. So when we get flooded, is the energy that is causing the damage, and in particular the kinetic energy, which is associated to flow velocity. If we, for the energy cycle, I want to give you a more quantitative discussion here in this slide, which is interesting because it gives an idea of the magnitude of these fluxes. And in particular, if we start with conventionally with a quantity of 100 of energy from the sun, and you see in the upper left of the figure here that we assume that the energy from the sun is 100, we see that about 20% of it, 19, is absorbed by the atmosphere, 4% is absorbed by clouds, and 23% is reflected back in the space by clouds, and finally 47% reaches the ground. And there is a part of it which is reflected by the surface, and it's 7% and goes back to space. Okay, now let's look at and this is the flow of energy from the sun to the atmosphere and the earth. If we look at the atmosphere, I mean, for any of these colors, so the flux from the sun to the earth is given in blue, and the sum should be imbalanced. So 100 should be equal to the sum of 47 plus 4 plus 19 plus 7 plus 23. Let's look at the atmosphere. There is a 49% of energy that is emitted by the atmosphere back in space, and there is a 9% that is emitted by clouds, and there is a 98, sorry, it's not percent, it's a mistake to say percent, I will explain you why. There is 49 over 100 that is emitted by the atmosphere, 9 is emitted by clouds, and 98 is transmitted by the atmosphere to the surface. So basically the sum of these energy fluxes out of the atmosphere is larger than 100, and therefore must be compensated by a similar quantity that is entering the atmosphere. And in fact, there is a 19% and 4% that is given by the blue arrows on the left. And there is a further contribution in terms of latent heat from the surface. I'm now looking at the brown arrows, and another 116 that is emitted by the surface and is split in 104 that goes to the atmosphere and 12 that is emitted directly to space. So you get here an idea. Of course, this is an approximation. It's just a very rough global average. You have an idea of the energy fluxes and how they are distributed. Okay, but if we want to describe these links, these fluxes, at the end of the story, we have to find equations, linear relationships. And so we have to describe the dynamics. It is complex. There are nonlinearities and there are tipping points. Let's explain what is nonlinearity, what is a tipping point. And these are extremely interesting concepts in general, because we have tipping points in the human body and also nonlinearity in the human body, for instance. So what is nonlinearity? Here you can see a mathematical definition, but basically we can define nonlinearity in a very rough way by saying that if I have two disturbances, the resulting impact in case of linearity is given by the sum or superimposition of the two individual impacts resulting from the two disturbances. It's like if I assume a dose of sugar and I have an increase, like I assume 10 grams of sugar, and I have an increase of my glycemia of sugar in the blood of like 3. And then if I assume other 10 grams of sugar, I have a second increase that is again 3, and the result is that 20 grams of sugar cause an increase of 6 in the level of glycemia of sugar in the blood. Actually, it's not like that. We know that the impact from two disturbances is not given by the sum of the two individual impacts of each one disturbance in a living system and in a natural system. Another example is when we have a proverb which says it rains over the wet soil, piove sul bagnato, which means that it's more disturbing. This means that when you get rain and the second rain is, even if it's the same intensity of the first rain, is more disturbing, is more impactful, which means that it's non-linear. And indeed, there are several non-linearities in the climate system. And another rough definition that you can give of linearity is that if you make a graph of like the variable, the progress of the variable in time, the graph is a straight line. This means that it's linear. And if you have instead thresholds, if you have exponential behaviors, if you have asymptotical behaviors, it means that it's non-linear. An example of non-linearity was mentioned by me at the beginning of the lecture today when I talked about the increase of the line cases after an increase of temperature. I said, look, it's not always 10% per each degree more of temperature. There is an asymptotic behavior. There is a max in the number of ticks, which means asymptotic behavior, which means non-linearity. This is why when we want to say that something is really tough, we say, look, this is non-linear. It's difficult to, it's easy to predict a linear process. It's just extrapolation of a straight line. It's much more difficult to predict a non-linear process. And what is a tipping point? A tipping point is, here there is an example, but I prefer to explain by word first and then to look at examples. A tipping point is a kind of a threshold in the state of a system such that if you pass it, you may get to a completely different state and it may be impossible to recover. So, to give an example, we know that in several situations, we may have a forest or brushes as land cover. And the transition between forest and brushes happens when you cut the forest over a certain extent. There is a threshold in the density of trees. If the trees are very dense, the brushes can't grow up because there is not enough light, not enough energy for them to grow up. If you start cutting the trees, if you cut a few of them, the brushes still can't grow up. But if you cut a lot of them, then the brushes start growing up and take the place of the tree, replace the trees. And if you want to go back to the previous situation, you have to make a manual intervention. They don't go back to the previous situation. There is not a natural evolution from brushes to forests. Or if it is a natural evolution, but it is very long, it takes a long time. So these are examples of tipping points. Typically, you have two equilibrium situations possible, and the transition between one equilibrium to another one happens by passing a pressure and then to recover may be very difficult. For instance, another example is the ice caps. We know that in the history of Earth, there were periods without ice caps and periods like now with the ice caps. What we don't know if is the speed of the transition. It is possible that the melting of the ice cap happens very rapidly. It is possible. And this may cause a sudden increase of the sea level, like a couple of meters in a few years. And what could be the motivation for this sudden collapse of the ice cap? First, we know from very recently, 10 years ago, we discovered that within the ice caps, both in Greenland and in the Arctic, there are hidden buried lakes, and there are some bubbles of water embedded into the ice. And the reason why this water is not frozen is the pressure, the high pressure of the ice. And this water is under pressure, actually, under the ice, and it's liquid. And we already observed some outbursts of these lakes because with the reduction of the thickness of the ice, it may happen that this water suddenly release on, they break the ice cover because it becomes very thin until it's broken for the pressure of water. And then suddenly you get these glacier outbursts. And we also had some over the Alps. You may remember in Courmayeur, I think it was some 15 years ago, when some people were flooded suddenly by the rupture of the sudden rupture of a glacial lake. So basically, what some people postulate is that if we reach a limiting threshold of warming, we may have the sudden release of water from the ice caps. And of course, this is only an hypothesis. We don't know it. There are several other examples, like the Amazon forests. You may have heard, there are several people who say we can't continue clear cutting it because if we reduce the size of the forest beyond a limiting extension, then we may run the risk of getting to a completely different equilibrium state. There are tipping points also in society. There are tipping points in economy, and we know them very well. Also in geopolitics, there are tipping points. There are revolutions. There are sudden changes of the equilibriums. There are wars, and these are tipping points. And they can lead to a completely new equilibrium. The revolutions typically they lead to a completely new equilibrium, and they are difficult to predict. So the big question is, if I want to make predictions because I want, for instance, to devise strategies for mitigating the risk associated to climate, what kind of models should I use? What kind of information should I use? And all of these issues, of course, must be taken into account when building models. And when building models, we are talking about mathematical models. What we do is to build a system of equations. And typically, we need a number of equations that is at least equivalent to the number of unknowns. So, do we want to simulate temperature? Okay, we need at least one equation. Okay. And I give you an example. So I jump forward with the slides. Oh, it's not here. So let me just go back. And I get it. Okay, just 1 second. Just 1 second, I downloaded another PowerPoint. So You can breathe a little bit, and I can breathe a little bit. Okay, here we are. This is the example that I wanted to, let me see. Okay. This is the example that I wanted to give. This is a very simple climate model, and it describes one unknown, and unknown is temperature, global temperature, okay, like the one that we explored at the beginning of the lecture. And what is the concept here? The concept is radiative equilibrium. So it's an equilibrium of energy, basically. Conservation of energy. Energy in terms of associated to heat. So what does this equation represent? In the left-hand side, we have the incoming solar radiation. S, capital S, is the solar constant. So it's the incoming solar radiation per unit area. It's about 1300 watt, so power, energy divided by time, watt per square meter. Okay, we know this number on average. Of course, it's different depending on the location, but on average, we know the amount. But we have to take into account the albedo of the Earth, so the amount of energy that is reflected back. And the albedo of Earth, you remember the numbers that we discussed before, we know is about 0.3, which means that about 30% of the energy is reflected back into the space. And then we have to multiply this solar radiation by the surface. So pi for the square of the Earth radius is the surface of the sphere of the Earth. Okay. And the right-hand side, you see temperature to the power of 4. And then you see the Stefan Boltzmann constant, which allows us to take into account the energy that is associated to each degree of temperature. And then epsilon, which is the effective emissivity of Earth. And then the volume of Earth. And therefore, by equating these two members, two sides, the right-hand side and left-hand side, we obtain an equation where the only unknown is temperature. So what is the result? If you plug in these numbers and you solve the equation, the result is given by this equation and gives a temperature of about 15 degrees centigrade, which is very close to the average temperature of Earth, which is 14.6 up to a few years ago. Now it's 14.8. Now, of course, it is amazing how this very simple equation gives to you a representation of the global temperature, but of course, keep into account that these constants, this average albedo have been a bit calibrated in order to, in a way, to optimize the simulation of this model. And this is something that is usually done. So in each model, you have parameters, so some constants like here, which allow you to tune the model to provide a better fit. And usually these parameters are calibrated, tuned. Okay? But this is a very nice example of a single model, of a climate model. Indeed, it is very simple. And the two considerations here. First, we are describing average temperature. We cannot describe internal variability. So we cannot describe the spatial distribution of temperature with this model. This is the first consideration. And why? because we consider the Earth as a whole, as a unique whole, okay? As a unique volume, which we analyze globally. This is the first consideration. Second consideration, what kind of relationship is this one? This is a conservation equation. It's a balance equation. And indeed, as we will see, the Earth system models, because the Earth system is a closed system, and because the Earth system is governed by the flow of matter, so the models are essentially based over conservation equations. So to give a first reply to my original question, how can we describe these links? How can we describe these fluxes? How can we describe tipping points? Okay, the most trivial idea that we can develop is conservation equations. And of course, they are formulated in a different manner depending on the matter, on the quantity that is concerned, for which we impose conservation. Okay, let's close this. And let's go back to this one. I think I have already, no. Okay. So these models then are, as I said, can differ depending if they are global, if they consider the Earth as a whole, or if they want to study the spatial variability. And basically, we can divide them in several categories based on different classifications. An important classification is based on the behavior of these models, and they, according to this classification, we can divide them in process-based models that are built by equations that are founded over a theory, like conservation equations, or we can use a more empirical approach and write empirical models, like, for instance, machine learning or like statistics. Machine learning, statistics, and to me they are very similar, but machine learning is gaining a lot of traction recently. So these models are forgetting about the theory, are forgetting about conservation equation, and they are just studying an input and output relationship in the same way in which we test the therapies in many cases statistically. So basically we make a testing, and with a statistical analysis, we analyze the results and connect the results to the behavior of the therapy. Sometimes we try a connection that is based on simulation. Also in medicine, there are fluid mechanics models, for instance, for studying the therapies for the reduction of cholesterol, etc. But in many other cases, we studied them empirically. And the result is that very often we can end up with a corresponding classification, which is very similar. It's a classification that splits the model in deterministic ones and statistical ones. So let me just explain this, and then we make the break. A deterministic model is one that establishes a one-to-one relationship between input and output. If you run the model twice with the same input, you get twice the same output. And typically, the deterministic model is based on the laws of physics, is based on conservation equations, where there is no uncertainty, because, as I said, same input, same output. This is deterministic. The statistical models, or stochastic, as it's called here, let's say for now that they are synonyms. So the word stochastic that I wanted to use here, because it's important that we know the terminologies, but it's essentially, we can say it's a synonym of statistical model. For a statistical model, you have not only a single output, you have a range of output. So for the same input, you get a range of output. Do you remember the progress of global temperature? There were the gray lines. It identified a range. This is an example of a statistical model where there is uncertainty. And uncertainty is the reason for the existence of the range. Okay. And the statistical models, what do we use to describe statistics? Remember, statistics is defined as the science that tries to get interpretation from numbers. You may have different theories to develop a statistical analysis. Usually we use probability, it's the most classical. It is boring because it's boring, but it is very powerful. And so very often we use the probability theory. And why it is boring? It is boring, I think, because probability theory is so rigorous that is based on a lot of theorems, a lot of demonstrations, and the notation becomes very heavy. And this is the reason why it's boring. But if you think the essence of probability is just trivial, I mean, think of tossing a coin and how many theorems we have developed in order to study the result from tossing a coin. But actually, it is just a science that tries to extract patterns from data. So it's very trivial, like when you see a graph and you try to figure out what's going on there. It's very trivial, actually, probability. But, you know, the science is a bit boring. And then I stop here. Let's start again after the break with this slide. Do you have any question? Okay. 15 minutes. Ok, allora vediamo di riprendere. Let's start again. How many hours of teaching on average do you have every day? Are you busy the whole day or yeah, morning and afternoon? Yeah, quite tough. Yeah. And you're attending the third year, correct? Mhm. And it's a 5-year program, correct? 6? Yeah, 6. Right. Mhm. Okay. I think you have some background in statistics probability, right? Yeah. Okay. And do you have some exams with on mathematics? Just curiosity, not because I want to make something. So, okay, not everything is calculation. Okay. Mhm. Okay, good. And you are already practicing at the third year in the hospital or not? In the second semester of the third year. Okay. Okay. Good. So we are talking about models, and I don't want to get to a mathematical description of these models. I just want to give an idea of how the models are structured. So I ask you information about what you study about mathematics, not because I want to get into more details, but just because I don't want to repeat things that you have already done. In fact, I am also coordinating with the teachers of ecosystems of the next year because I want to avoid repetition as much as possible. Okay, so this figure is just a summary, a graphical summary of the difference that I mentioned between deterministic and stochastic models. And this figure also says that it's possible to make a mix of the two. And this actually is the ideal solution when dealing with physical processes in the presence of uncertainty. The best solution is to mix the knowledge with a treatment of uncertainty through probability. And there is a lot of research on this, and also a lot of research on conditioning the output from machine learning models. Machine learning models, as I mentioned earlier, are getting a lot of traction recently because indeed they are simple to use, they are very quick and fast, and indeed when there is a lot of data available, when the data set is extended, then these models are very quick and give also very good interpretations of the underlying processes. But also in this case, there is a lot of traction on methods and solutions for conditioning the results from machine learning. We already talked about uncertainty assessment, and therefore I'm not going into more details. And also we already talked about perturbations, and there are several perturbations that may occur into the Earth system. And the human activity is just one of these perturbations. And of course, what we have to care about this perturbation is the potential capability of switching the state of the system through a tipping point. And therefore, I mean, the assessment of tipping points should also be done through a consideration of the external drivers and the actions and the perturbations to which the system may be exposed. When we talk about human perturbations, so anthropogenic influence, human activity, very often we assume that it's the only perturbation that may exist over the natural system. Actually, the natural system is subjected to perturbation. And the natural system is the result of an equilibrium that have been reached against several different perturbations. The natural system is, by definition, resilient, because otherwise it wouldn't be a natural system. And the natural system got to this state, which is a state that is governed by some form of equilibrium, because it survived selection that is related to the perturbation. The natural system survived to a series of perturbations, and it's a system that is, once again, naturally resilient. But very often we tend to assume that nature is a perfect world, is a world without perturbation, and any perturbation that happens, we tend to attribute it to the human influence. So anytime that we get flooded, anytime that we get a cyclone, anytime that we get a new disease, we try to attribute the responsibility to humans, and we forget about the perturbation that may naturally occur. We know that there is a natural selection, and so it's not it's something that goes through competition, through resistance to perturbations. The fact that we forget this natural perturbation is not good, because in order to solve a problem, we need to know the causes. And if we ignore natural causes, natural perturbation, we miss opportunities. And also, it's not good because the natural perturbation interact with the human perturbation. So the human perturbation of climate may be not concerning in situation where nature has the capability to recover, where the human perturbation is negligible with respect to the natural perturbation. But there are other situations where even a small perturbation by humans may interact with the natural perturbation and create a positive feedback, and therefore overall degradation of the state of the system. Talking about perturbation, for instance, I would like to mention the secular variation of the magnetic field. The magnetic field, we know that, has been subjected during the history of Earth to several reversals. A reversal of the magnetic field means that the South Pole switches with the North Pole, and therefore the compass changes the orientation. And we know that these events occurred in the past with a frequency that on average is about 450,000 years. The last one occurred about 800,000 years ago. So it is expected in our near future that we may undergo an inversion of the magnetic system. It's not something that may cause the mass extinctions, but still it is something whose consequences, even on the human health, are largely unknown. So what I mean to say is that we don't have to think that nature is a perfect world which is not subjected to perturbation and the humans are the only ones to blame. But we have to get, once again, an integral perspective, an holistic perspective. Okay, now let's go into more details about the models. And before I switch to the next lecture, let me just close this PowerPoint, which is not necessary anymore, and let me open the web form of this lecture, because as you know, I am using the PowerPoint, but here we are. I'm using the PowerPoint, but there is a web version that is much more detailed. And therefore, let's go here and let's go here. The Earth system. In this lecture about the Earth system, which we just discussed, and you can recognize the figures of the PowerPoint, there is a box that I didn't discuss with you, which is related to the theory, the basic theory of conservation equations. It's here, and I don't make any comment. I think that if you are interested in how these models are structured, this may be an additional information that may be very useful, because I made an effort to make it very simple. And these conservation equations are very simple at the end of the story. What makes them complicated is the number of equations, but they are very simple, and they are based on a theorem which is called the Reynolds transport theorem, which is the basis for any model of the Earth system. Here it is, the link. The link is at a Wikipedia page, which is, by the way, quite complicated. So I made an effort in my webpage to make it simpler. I just wanted to explain to you that if you decide to study the lecture on the web, you will see this part that is I have not introduced, because I don't want to go into mathematical details that may be a bit too much demanding, but still an information that may be useful. Okay, now let's move to the next one, climate models. And here I get to the PowerPoint, which I just downloaded a second ago. Before we talk about climate models, I want to, let me see, because I think this figure is in the PowerPoint, so it's better. I want to make a premise on water, which is an important premise for the implication on Earth. Okay, here is the important premise. So this is a sketch of the distribution of water over the Earth. It just looks at the average storage of water. And there are some of my colleagues, this is a very popular figure, some of my colleagues are very critical against with respect to this presentation. Why? Because they say this is a static representation. It doesn't represent flows, but still I think to get an idea of the quantitative state of the water system is interesting. And then while we discuss this figure, I will explain to you why neglecting the fluxes is a limitation. But let's move from the left column to the right column. The left column is a focus on the global distribution of water. You see, total global water. First important consideration, salt water is more than 97% of the total. And this brings in light the potential of desalination. Again, salt water in the ocean is 96.5% of the total, plus a 1% of other saline waters, which are salted waters, which are, for instance, included in internal seas or in marshes where there is an increase of the concentration of salt. So fresh water is only 2.5% of the total. Still, there is water for everyone. So this 2.5% covers the needs of the whole humanity, not only in the current numbers, but also in perspective. If there is an increase, a further increase of population, I mean, there is water for everybody. But you may say, and so what is the reason why some people are suffering from lack of water? Yes, there is water for everybody in terms of total volume. But again, the global picture doesn't describe internal variability and doesn't describe, in this case, the time variability. So there is water for everybody, but not everywhere and not every time. So it's the spatial distribution of water that is such that there is a lot of fresh water, abundant fresh water, for instance, in Sweden, in Finland, they have a lot of water, and to this abundance corresponds a lack of water in some countries. And also the spatial distribution is sometimes, the temporal distribution is sometimes a problem. And therefore we may have a lot of water where when time we don't need it, like winter, and less water when we need it. So what is the moral of the story? When you think about perturbation of the water system, climate change is for sure perturbing the water system, you have to consider the current state of the water system. So a perturbation of the water system is not a big problem in Sweden. Maybe a problem in the south of Italy, where the water resources are already a bit scarce. In general, the northern central Europe doesn't suffer from water scarcity. The south of Europe, the extreme south, I mean, from in Italy is about from Naples to the south, we have some problems. Second consideration related to water, which is not very much known. If you look at the global water uses, 70% of it at the global level, and more or less we have the same percentage in Italy, to what destination is dedicated. So what is the major use that we make of water is not very much known. It's water for food, it's agriculture, it's irrigation. So 70% of the water use is agriculture. About 15% is less than that, 12% is civil use, so for us, and about 20% is industrial use. And these percentages are more or less the same in Italy. In Italy, agriculture is a little bit less, it's about 62%. And then the remaining 40% is about 25% industries and 15% civil use. So you understand where water needs to be saved. It needs to be saved everywhere, and also in our own tap. But the most important thing is to look at agriculture, and agriculture is water for food. And this is why we talk about water, food, energy nexus. I would also add the economy, money, so water, food, energy, money nexus. It means that all of these entities are strictly related to each other. Now, the central column here is a zoom over the fresh water. The fresh water, you can split it in the categories that are depicted in the central column, which refers only to the 2.5%. So we have about 70% of the 2.5%, that is water stored in glacier. It's fresh water, but it's stored in glaciers and ice caps, so cannot be used. The water that can be used by humans is about 30% of the 2.5%. So it's about 1% of the total. And this water is divided in groundwater, 30% of the 2.5%, and surface water and other fresh waters, only 1.2%. And now the consideration about fluxes. This depiction doesn't give justice to the importance of surface water, which is water flowing into the river. Why doesn't give justice? Because its in volume is very reduced. If you take the water that is stored in the Po River and you compare it with the water that is stored in the Garda Lake, it's of course negligible. I mean, because the storage in the Po River is not as much. It's, you know, it's when it is very deep, it's like 15 meters deep and 100 meters large. The Garda Lake is, I think the perimeter is about 200 and something kilometers. The storage in the lakes or the storage in groundwater is much larger. But in the Po River, water is flowing, and therefore the amount of water that I can get from it is much larger, because if I get water, it doesn't get depleted. The water flows back, and after one day I can go there and take the same amount of water. In a lake, of course, and especially in groundwater, the flow is very low, and therefore the storage is not representative of the potential of this water body for use by humans. Because we have to be very careful in using groundwater, because groundwater gets a long time to be replenished. And also, the fact that the water is flowing is an indicator of quality. And it means that if the body gets contaminated, it's easier to recover it. Now, right column, it's a zoom over surface water. And so it's a zoom on the 1.2%. And we can recognize that there is a ground ice and permafrost. It is, again, 70% of it. And then there is what we can use, lakes, 20%, 21%, soil moisture, rivers, swamps, marshes, living things, 0.26%, and atmosphere, 3% of the 1% of the 2.5%. Okay, this is a picture that gives the state of the a picture on the state of the water system in terms of storage. And keep in mind the connection between climate and health is through water. It's waterborne diseases are those that are a real matter of concern for us. In the previous years, I was used to dedicate a lecture on the waterborne diseases. Now I learned that in ecosystems, they make the same lecture, and therefore I delegated them to deliver this lecture. Now, so let's look at the climate models. I think we already discussed the fact that is driven by the solar energy, the climate system, and the fact that part of it is reflected back into the space. And then I think this premise is not necessary. It's also not necessary, this slide, because it gives some explanation of complexity. And let me instead focus a little bit on this, because this deals with the chaotic behaviors. So far we talked about complexity, we talked about tipping points. Now let me just focus on the chaotic behavior. What does it mean, chaos? This picture reflects turbulent, it gives an idea of a turbulent process. Is the vortex originated by an airplane by an airplane wing. Turbulence is a clear example of chaos. Another clear example of chaos is the butterfly effect, is the say attributed to Lorentz in the 1950s, I think. The say that states that a movement of the wing of a butterfly in Japan may cause a tornado in New York. What does this mean? It means that a system, typically a nonlinear system, may be very sensitive to initial conditions and boundary conditions, which means that a small perturbation very far away or very far in time may cause a huge development, a huge change after a long time or after a long space. And therefore, the consequence is that the evolution of the process is almost unpredictable, close to unpredictable. And turbulence is such an example. Turbulence means that these processes is governed by processes taking place at the microscopic level, and therefore making a prediction of the evolution of these vortexes is almost impossible. And this is chaos. Chaos is governed by deterministic equations, but still they are unpredictable. Because, I mean, if you think about cyclones, it's a physical process. But if you think also about tossing a coin, it is a very trivial example of chaos, because it's a physical system, but we can't describe it. We could describe it in deterministic terms, but it wouldn't be successful, because tossing a coin is very sensitive to initial condition. So when I flip the coin, even a small change of my hand in the position can change the final result. And also a small change in the energy that I give while flipping can change the final result. So it is an essential component of the Earth system and of climate, which makes it unpredictable. Okay, so let me just show you this figure, and then I describe what is reported in the previous slide. So this is a depiction of the Earth system, of the Earth globe, which is in a way split into a grid, or better, elementary volumes. Over the surface, you see a grid, but to each grid over the surface corresponds a depth in the system, and therefore it's split in elementary volumes. Why do we split in elementary volumes? Because I mentioned to you that when we apply a model by considering the Earth as a whole, we describe the average of each quantity, but cannot describe the internal distribution. So if I want to describe the global temperature, I can avoid this grid. But if I want to describe the temperature in Milan, then the global representation is not possible, because I can't, from the global representation, get the detail of what's going on in Milan. And therefore, I have to make a different approach. And why I have to adopt a different approach? Because there is spatial variability and there is time variability. Internal spatial variability, and with space, I mean the three directions, not only the surface. So there is variability also along the vertical. So when I get in the underground, there is variability, the temperature is different, and etc. And there is time variability. And therefore, I need a local description. If I want to explain this variability, I need a local description. And the local description means that when I apply a conservation equation, I don't consider the Earth as a whole, but I have to consider an elementary volume, embedded in Milan. So I take like a grid cell of 3 kilometers by 3 kilometers, or 5 kilometers by 5 kilometers over Milan, and then this cell is expanded into the atmosphere, and I write the same energy balance for computing temperature that we saw at the global level. I apply it on this elementary volume. So each of the elementary volumes that you see here, over the surface, in the atmosphere, and also in the depth, they need to be modeled individually by a given system of equations. The problem is that these are not closed systems. So if I isolate a volume, including the atmosphere, over Milan, I cannot separate. The system is not closed from the analogous system with respect to the analogous system that is over Monza. It's not isolated. There is not a barrier to energy between Monza and Milan. There is a flux of energy, and there is a flux of any other matter that I model with the climate model. And therefore, I have to describe these exchanges. And this means that the solution of the elementary volume over Monza depends on the solution of the elementary volume over Milan. And if you consider that these elementary volumes in the last generation of models are about 25 millions, you understand that if for each elementary volume I have 10 equations, I have to solve at the same time, contemporary, 250 millions of equations. And so you understand why we need supercomputers. And you understand why people started with very coarse resolutions. So they started with 100 kilometers by 100 kilometers, and then went down to 50 by 50. And now, if you look at the Copernicus data store, you find 5 by 5 kilometers resolution at the global level. It means that at any grid cell, you have only 25 square kilometers represented, and you have enough grid cell to cover the whole globe, and also the atmosphere and the underground, because each column cannot be modeled with only one layer. You need several layers. I made a model of the groundwater flow in the Emilia-Romagna region, and we adopted 35 layers to describe the underground, because in order to get a description, a rigorous description of groundwater flow, we needed 35 layers up to a depth of about 300 meters. And so each layer included a depth of about 10 meters, with exchange of water between one layer and the layer above and the layer beneath it. So basically, we have to run these models in a supercomputer. And also you understand why perturbations or initial conditions may be so relevant, because when you pass from one cell to another cell, the approximation may explode. What is a further complication? That these conservation equations are expressed in differential form. What does this mean? That they include derivatives. Why do we need to include derivatives? There are mathematical explanations, but I like to give a very simple explanation. If we want to describe flows into a given volume, we have to take into account also the change in storage, because it may happen inside the volume that the inflow is larger than the outflow. So if I want to compute the outflow based on the inflow and many other conditions, like the geometry of the system, I also have to take into account changes in storage. What is a change? Is a delta, is a difference, is a derivative. And therefore, if I want to describe the change in storage, I obtain a differential equation. What is the problem? It's not really a big problem. The problem is that we need an integral. That is something that is a bit nasty. If we want the integral is what we need to pass from the differential form to the value of the variable. So if I describe the change in storage, at the end of the story, I need a number for the storage. And if I want to get the number for the storage, I have to take the sum of the changes. And the sum of the changes is the integral. And I need an initial condition. Initial condition means that I have to know the storage at the beginning. Because if the equation describes only the change in storage, I have to start from a known baseline. And this is the initial condition. And I also need the boundary condition that are the fluxes coming from the nearby, the neighboring elementary volumes. Today, integrals and derivatives are not really a matter of concern because we have supercomputers. But they add to the mathematical complexity. So you understand, hundreds of millions of equations in differential form that need to be integrated. This is why we need supercomputers. And this is why we produce so many data. This is why I need a code to access the climate database of Copernicus, the climate data store. And I mean, it's really a complicated story. And then consider one thing that adds to complexity. This idea that we have, which is fully motivated, to adopt an holistic perspective, which means modeling these systems together, means that a climate model should not only describe climate. It must include a representation of the water cycle. It must include a representation of the carbon cycle. And therefore, these models are today called, with a more general terminology, Earth system models, because they try to describe the whole of the Earth system. Okay, so we already discussed about conservation equations. So basically, conservation equation of carbon, of water, of energy, of mass in general. Take into account that there are nuances, of course. Some of the quantities may degrade because they are subjected to natural degradation, and therefore you have to take into account also the fact that you may have lost terms Like for water, for instance, we consider deep percolation. There is a part of rainfall that goes in the deep underground and then emerges back after maybe thousands of years. And these are contributions that need to be accounted for. Let me just say one, and I prefer, let me just see. Okay, yeah. I already discussed about the supercomputers, so this is fine. And there is one thing that that I want to discuss, and let me just jump forward. I want to get a video which it's not here. Just 1 second. I get it's in the web page. Let me just go here. Okay, this is what I wanted to show. Okay, what you see here, these are Elysian scenarios, and with this there is something wrong. Just 1 second. Okay, emission scenarios. Climate models, of course, vary. And the input is, for instance, the energy from the sun. The input is the geometry of the system, the shape of the system, and one fundamental input is the CO2 concentration in the atmosphere. It's you understand the reason why it's a fundamental input. We attribute much of the human influence over climate to the human emissions of carbon. And human emissions of carbon that derive from several activities. We will try to see, we will see a figure that attributes to the most important in terms of carbon emission human activities percentages of contribution. I anticipate that energy production is about 70%, but in energy production, so this means that 70% of the human emissions are related to generate production and energy production. And energy production, by the way, includes also transportation, which, however, is a reduced amount because energy transportation means production of energy. But human emissions are basically of CO2 are those that are considered the most important in terms of human influence over climate. And these human emissions are related to our socioeconomic model and our socioeconomic development. And there has been an increase of human emission from the pre-industrial level that has been really massive. It's not easy to quantify human emission of CO2. Usually they are indirectly estimated from measurement of CO2 concentration in the atmosphere. However, there are several other sources of emission, like for instance, the oceans. In reply to a warming, the oceans release a lot of CO2. They host a storage of CO2. They can originate a CO2 sink that is very relevant. And but of course, by using appropriate assumptions and models, we can estimate the human emissions depending on the CO2 concentration. We know that the CO2 concentration is increased a lot from the pre-industrial times, and then we estimate what comes from humans. And then the big issue is that if we want to make a prediction of the future climate, you have to make a prediction of human emissions. And there are several so-called emission scenarios that have been proposed for the future, based on different assumptions of mitigation policies and human development. First, as you know, a lot of emissions are related to the increase, a lot of additional emissions are related to the increase of human population. But there is also a relevant role that is played by mitigation policies. Here, what you see is a depiction of human emission curves starting from 2015, if I'm not wrong, because these predictions have been updated in 2013. And you see with continuous lines, the previous predictions, the predictions that were issued by the assessment, the third assessment report of the IPCC. With dashed lines, you see the predictions issued by the fifth assessment report of the ICPP. Recently, is being released in these weeks, the sixth assessment report, which provided a further update. What you can see here is that the dashed line are a bit more optimistic. Indeed, we realized that we overestimated the human emissions in the past, and the different colors correspond to different assumptions in terms of mitigation policies. The red lines are called business as usual, which means that we continue not to care about human emissions, and therefore they continue to increase up to about 2080, and then it is predicted a stabilization for many reasons, including the fact that fossil fuels are going up, being depleted. And then with the yellow line, you see a more optimistic prediction, which is based on a partial success of mitigation policies. And then there are other lines, other two lines, which are even more optimistic. And here, the prediction is based on the anomaly. So you see negative values because they refer to a zero that is an historical value of human emissions. What kind of scenario should we adopt? The European Union suggests that we stick on the business as usual. In the United States, some governmental agencies instead suggest to adopt the yellow scenario. You see that these scenarios, but the most pessimistic is always increasing. The other ones predict reaching a cap. A cap, it means a top of human emission after which we will start to decrease. And this cap has been predicted to occur, depending on the prediction, between 2030 to 2060, 70. Actually, there are some recent researchers that have estimated that we are very close to the cap, but the argument is a bit debated, so there is some discussion about it. These are essential inputs to predictions. So keep in mind, when we talk about climate change, climate scenarios, prediction for the future, these emissions have a relevant, play a key role. Okay, I would say see you next week. Questions? Enjoy your weekend.